All right, good evening, everyone. In this lesson, we're going to be looking at momentum. I find that momentum is one of the sections that a lot of people struggle with purely because of two reasons. They either don't understand what momentum is or they forget to use directions, one of the two. All right, so I'm going to start by sharing the screen. Okay. All right, so ladies and gentlemen, sorry, full screen. There we go. Just going to move that down so that I can see all of you. Okay, brilliant. So I remember when I was in matric and we looked at momentum and the teacher came out and they said, what is momentum? And then came the wonderful definition that momentum is the product of mass and velocity. And I remember, ooh, it's not behaving very nicely there. Let's try and spell velocity so that it looks like velocity. I remember looking at it going, yeah, okay, so momentum is the product of mass times by velocity. But in my head, none of that seems to actually make any particular sense. So with regards to momentum being the product of mass and velocity, I'd go, yeah, okay, and there's nothing wrong with taking the equation and saying P is equal to mv. But the problem is that if you don't know or have a picture in your head, it gets a lot harder to make sense of what it means when we say momentum with the units of kilogram meters per second is equal to the mass with the units of kilograms times by the velocity in meters per second. So I have a slightly different way that I explain this. And that is that I, instead of looking at momentum as being the product of mass and velocity, I look at it in terms of the English definition. Now, who here knows what momentum is if we're talking about English? So if we're talking about momentum in English, what do we mean when we say momentum? Okay. I know that one of the places where I knew about momentum from in school was that momentum was something that things gained. And you could talk about a political party or an idea or a movement gaining momentum. And the same applies to when we talk about momentum in physics. So I regard momentum as being a measure of how difficult it is to change or stop the motion of something. So if something has an exceptionally large momentum, you're going to find it very difficult to change how it's moving. All right. So when we go back now to look at my whiteboard, I'm going to hopefully find that this makes a little bit more sense. So an object will have a large momentum and be difficult to change its motion if it either has a large mass or a large velocity or both. So if we deal with an object having a large mass, like a steamroller, it will have a large momentum. You will not want to be the person standing in front of it trying to stop it with your body strength, because you're going to end up being flattened like a pancake, okay? Because it has a large momentum because of the mass. Same thing with charging elephants. Charging elephants, charging rhinos, you get out of the way because they have a large amount of momentum. Even if they're not traveling very fast, their mass gives them momentum. Same thing with rugby players, okay? If you have something traveling at a large velocity, even if it has a small mass, think about a bullet fired from a gun, that is going to have an exceptionally large momentum. Once again, don't want to be the person in front of it trying to stop it, okay? If you had something with the mass of an elephant traveling at the speed of a bullet fired from a gun, you're in very big trouble. So that is the idea I have when I talk about momentum. It's literally the product of mass and velocity, and all you've got to do in order to get it right is make sure that your mass is in kilograms and your velocity is in meters per second. Now, I know it sounds a bit crazy. Every now and again, they do actually even give you a really, really easy question where it's, here's the ballet dancer, they jump up, they come down, what is their momentum? And you go, oh my goodness, when they come down, the 50-kilogram ballet dancer is traveling at 3 meters per second, so we multiply the two together and we get our momentum. The last thing that's very important to remember here is that momentum is a vector quantity. Since it is a vector quantity, that means that you must always put in a direction. Now, sometimes you get out of the clause of needing to put in a direction, and that's if they ask you just for the magnitude of the momentum. If you've just been asked for the magnitude, then it's nice and easy. All right, ladies and gentlemen, I think that this aspect of momentum so far hopefully is very nice, clean, and easy for you. It's also something that I think a large number of schools covered a very long time ago, so it should actually be something that you're beginning to get comfortable with. So, stopping here at a very basic level, I'm going to give you a quick calculation. So we're going to deal with a rugby player. So we're going to say a rugby player of mass, will be nice and make him reasonably fit, 90 kilograms, is running, we'll even be specific, is running south. I don't think many people on a rugby field can tell which way is south, but it's okay. Not to be mean to the rugby players, just because I'm very bad at, I can't even tell you from here which way is south, but he's running south at, let's make him relatively fast. The fastest that most humans can run is 10 meters per second, and that's kind of Usain Bolt racing. So here, let's make him relatively fast. He's running at 7 meters per second, okay? The question here could be to calculate his momentum, which, yes, is the product of his mass and velocity, but more importantly, it's a measure of how difficult it will be to stop him and how you don't want to be the person that's standing in the way of him, unless, of course, you're also a rugby player and you're going to try and tackle him. Ladies and gentlemen, can I quickly ask, I paused my screen, can I quickly ask you, it's a super easy calculation. It should take you just a second. I'd like you to quickly do the calculation. Remember, formula, substitution with units, and answer. Okay. Can I ask you to please give me a thumbs up when you have got your answer? Good. Okay, I think at this stage we should safely say that everybody should be able to do this, because this is the dead easy bit. It only gets harder from here, but the point is, if you can't do this little bit, then we're going to have bigger issues. All right, so ladies and gentlemen, I'm going to resume sharing. Okay, some of you have given answers, but we've got to be very careful because we're getting closer to our matric exams now. We're at the point where I'm going to start getting really nitpicky about the places where you're going to lose your marks. So, first mark is for formula. P is equal to MV. Second mark is substitution, 90 times by 7. And then the third mark is likely to be for 630. But if you don't have kilogram meters per second or south, you can lose that last mark. Sometimes we are super generous and we give you a mark for that and then a mark for south. And it actually gets a bit crazy, but you can get the mark for south even if everything else is wrong. So the south mark or the direction mark can actually be a mark in isolation. So if you're ever completely confused as to how to answer it, but you know which direction it's going to be in, make up a rubbish answer. Obviously, only make up the rubbish answer if you can't put down a proper answer. And then write south at the end, because you can get a mark for that south. All right, ladies and gentlemen, who got that correct? Thumbs up if you got it correct. I'd like to think it's most of you. Okay, fantastic. I'm glad that so many of you are doing the exercises, even though they're relatively straightforward. So that is the idea of what momentum is. Now, if momentum were that easy, none of you would be coming to the extra lessons in the evenings. So what we're now going to do is we're going to talk about other things that link to momentum. And the first thing that we're going to do is we're going to talk about the change in momentum. Just quickly checking, everybody's got what I've written down here. I can clear the screen. Okay. The next thing that we look at specifically is the idea of a change in momentum. I could do this with a ball hitting a wall, a ball hitting a ground, two cars colliding, anything where there's a change in momentum and an object changes its product of mass times by velocity to another product of mass times by velocity. One of my favorite ones to do is we have got a ball, it comes in and it hits a wall, okay? So I've got a ball. I'm going to tell you that the ball has a mass of 0.2 kilograms. Please bear in mind that I may have given this to you as 200 grams and you'd need to convert. Is there a question? Okay, so if I gave you the 200 grams instead of 0.2 kilograms, you'd need to convert it first. Let's say that this comes in and it hits the wall and it's traveling at 13 meters per second. Quite fast, but I'm no expert on tennis balls, so we're going to pretend that it's normal. Then the ball hits the wall and it rebounds outwards, and when it rebounds outwards, it's traveling at 10 meters per second. So the first thing that we're going to do is we're going to talk about change in momentum. The symbol for change is delta. Your momentum already, you hopefully know, has the symbol lowercase p. So my change in momentum is going to be the final momentum minus the initial momentum, which means that we can say that my final momentum is going to be my mass multiplied by my final velocity, and my initial momentum will be my mass multiplied by my initial velocity. Some people choose at this point to say that for almost all questions, your mass doesn't change during the collision. We like to simplify it so that it doesn't. So here you can say final velocity minus initial velocity times by mass. Any one of those is technically an equation, and you could use either of those as well. All right. Now, ladies and gentlemen, I told you right at the beginning that momentum was a vector quantity. Because I want to see how much you all know before I give you the answer to this, I'd like all of you right now, looking at this example with the ball of 0.2 kilograms coming in, hitting the wall, bouncing out, I would like everybody to please work out for me what the change in momentum of the ball is. To make life easy and as a super bonus hint, I'm going to hint that you make towards the wall positive. All right, can I please pause my share? And while I do that, I'm going to encourage all of you to quickly do the calculations as well. If you wish, you can use the directions as positive and negative or towards and away from the wall. Please go for it. Okay, when you've got an answer, you can just give me a thumbs up. Good. Good, good, good. All right. I think most of you by now have had your thumbs up, so I'm going to quickly keep going. So what I did here was I used the last equation. Please note, I'm counting that as part of my equation. Otherwise, I've left off my formula, and then I'm in big trouble. So my mass here was 0.2 kilograms. The final velocity was 10 meters per second, but it was away from the wall, so I had to put in negative 10. Minus came from there. Then it was the initial velocity, which was 13 meters per second towards the wall, so it's positive 13. So I actually over here have a change in velocity of negative 23. You don't have to work out that it's 23 there. You can just plug it into the full calculation. And that gave me an answer of negative 4.6 kilogram meters per second. The negative is just for a direction. Please remember, this is us going back to vectors, where the negative tells us that it is away from the wall. So where many people go wrong with this is they put in this is positive and this is positive, and they don't figure out that it's actually changed direction, and therefore we've got to actually deal with a change in momentum. We can't assume that it just stays the same, and we can't leave it as just staying the same. I've seen a couple of multiple choice questions where they ask you to draw a vector diagram. Or they even have a question where they'll say, which of the following represents the change in momentum? So I'm just quickly going to clear here And I'm going to show you a typical kind of example. So if I clear all the drawings and I do something similar, and I tell you that the object comes in with a momentum P and maybe gets hit and bounces out with a momentum 2P, and they ask which of the following, A, B, C, or D, could be a possible vector diagram. So I have something that looks like this, that's got P, 2P, something that looks like this, and it's got P, 2P, something that's got a P and then a 2P. I'm of course making this up. There's a very good chance that I mess it up completely. And then there's a P and a 2P or something like that. What you've got to realize here is that our change in momentum is the final momentum, which means change in momentum is the final momentum minus the initial momentum. So I have to have my final momentum in the direction it goes. So my 2P has to be going towards the left. So that's a possibility, that's wrong, okay? So immediately D and A are out. Then my minus my initial momentum, the minus flips the initial momentum around. So if it was going that way, its direction effectively inverts and becomes opposite. So here the answer is B. And a lot of people get very confused with graphical representations like this because you're not really used to it. All right. So ladies and gentlemen, that was us just very quickly looking at the idea of change in momentum. Now, the next question that I need to ask all of you is what causes the change in momentum? So we've got an object and its momentum changes. Like you just saw when we had the example of the ball hitting the wall and bouncing back. What causes this change in momentum? And the answer is the thing that causes the change in momentum we call impulse. An impulse is the product of an applied force and the time for which it acts. Now, keywords here, you've got to have the idea that it's force and time, but more importantly, that it's the product of the two. Impulse itself doesn't have a symbol. So a lot of people who don't know what they're doing suddenly bring all these I's to the table. Like you end up with uppercase and lowercase I's, people going, oh my gosh, it's impulse, it has a formula or a symbol. Impulse has a symbol. Its symbol is F delta T. And our rule with regards to how we get this impulse is that F delta T is equal to delta P. Basically what that says is that impulse is equal to your change in momentum. This means that you can link these two together directly. That means, like if you're a tennis player, okay, now you'll very clearly hear that I'm not a tennis player very shortly, but if I'm a tennis player, if I were, and if I wanted to hit that ball when I served the ball with my tennis racket, I would make sure that I did a follow through and that the ball remained in contact with the racket while I was exerting a force for as long a time as possible. Because if I exert the force for as long a time as possible, I will get a bigger change in momentum, which means that when the ball leaves my racket, it will be traveling faster. So sometimes you want a big impulse to cause a big change in momentum. Sometimes, on the other hand, we actually like to use this to instead reduce the force that something acts, or for how big a force we get as something changes momentum or acts on another object. So if impulse is equal to change in momentum, what is the difference between the two? Well, quite simply, it comes down to their units. Change in momentum is measured in kilogram meters per second. Impulse is force measured in newtons multiplied by time, which is measured in seconds. I know that a lot of you have gone very much into the habit of having per second. Please, there's no to the power of -1. This is newtons times by seconds. The big difference is if on that previous example where you got an answer I think of 4.6, I'd asked you what is the impulse. Instead of saying my change in momentum is 4.6 kilogram meters per second away from the wall, you could instead have said that the impulse on the ball was equal to 4.6 Newton seconds away from the wall. All right, so we briefly touched on what impulse is. I want to just quickly do a derivation of this from Newton's second law and show you that this is actually Newton's second law. And then after that, I'm going to look at a couple of practical examples that they like to bring up when you do this section. All right, but before I do this, can I just double check? Is everybody still with me? Does this make sense to everybody? I also wanted to ask, just quickly hands down, I'm getting lots of yay, it makes sense, which is a good sign. But I wanted to just quickly also ask over here, hands down, who had never fully understood what momentum was because it's mass times by velocity, and they'd never had a picture in their head of what momentum was linked to? Is there anyone here who felt that way? Where you kind of had momentum, but we spoke about it and we didn't know what it was? Okay, that's good. It's actually surprisingly few of you, which is a very good thing. I find that sometimes it's one of those sections which is understood in isolation, which becomes very tricky. All right, so I told you that the equation F delta T is equal to delta P is Newton's second law. Now, most of you know Newton's law and as F net is equal to m times a. The resultant force is equal to the mass times by acceleration. Now what we're going to do is we're going to expand acceleration. Acceleration is the final velocity minus the initial velocity over the change in time. Okay? I can then take my change in time across to the other side and kind of drop my F net to just becoming F. It's still the resultant force, but we're just going to say it's the force now. And then I'll have mass, final velocity minus initial velocity. If you wish, you could probably already see that as a change in momentum. If you need me to instead break it down even further, mvi, or p final minus p initial, or the change in momentum. So this equation is a different version of Newton's second law. And in fact, it's one of the places where we get the definition of a force from. There's another one that we also sometimes use, where we can say that the force is equal to the rate of change of momentum. Okay, now I just want to point out to you that this is going to come up often as an option in a test. And quite often what they do is they say force is equal to the change in momentum, and everybody jumps on it because they're like, oh, I know that looks familiar. Please note it's got to have the words rate of change. Okay, so you can't just have force is equal to the change in momentum. It's got to be the rate of change of momentum. If you leave off that rate, you're leaving off the time, and then you're saying that force is equal to this part, which it isn't. So we can sometimes rearrange it and say force is equal to the change in momentum over change in time, which is basically us taking this equation and moving the time down to the denominator over there. So what does it mean when we say that the force is equal to the rate of change in momentum? It means that if you change your momentum very quickly, then you must have a large force being applied in order to do this. And quite often we have two objects, or there's a collision, or there's a wall and an object. And you must also remember that Newton's third law holds. If this object exerts a force, or if the wall exerts enough of a force on the ball must exert an equal but opposite force back on the wall. So in terms of remaining safe in traffic accidents, one of the things that we want to do to remain safe is we want this force to be as low as it possibly can be, which means that you can't really change the fact, okay, you could drive slower, but let's pretend you're traveling at 80 kilometers an hour and you have a collision and you're brought to rest. One of the ways that we can reduce the force that acts on you during that collision, we can't really change the momentum. We can't really change the momentum. You were traveling as fast as you were, you usually come to rest, and hopefully, well, your mass should stay the same during the collision. We like to make things neat. The easiest way for you to decrease the force is to increase the time. That means that if we can increase the time that it takes for a collision to occur, we can reduce the force and make everybody safer. So, a couple of the things that you'll notice. We wear seat belts to hold us in as part of a car. However, one of the things with seat belts is you'll notice a large number of seat belts initially have a small amount of give before they suddenly lock you in. That small amount of give can increase the time. If you have airbags, instead of you going and hitting the steering wheel in front of you, it's not that they're soft or anything, it's that they cushion you in. So instead of you going rapidly in, you go slowly in. Slowly is still a very, very, very fast speed in a very short time, but it's about 10 times longer than if you didn't have an airbag. We also use crumple zones on a car because the crumple zones, people always say crumple zones absorb the impact. It's not really that they're absorbing the impact, it's that they're increasing the time that it takes for everything to come to rest. Okay, a little bit of a crazy idea. If you drop a coffee mug and you drop it onto two different surfaces, so here's my poor little coffee mug, and I happen to have two bits of floor. This bit over here is fluffy and is carpet. This bit is tiled and is hard. Most of you would go and tell me that the cup would break on the tiled floor but not on the carpeted floor because the carpeted floor cushions the impact. While this is true, if we come at it from a physics perspective, we should actually say that in both cases, because it's falling from the same height, the cup will hit the ground with a certain velocity. Usually it's, sorry, that should be initial velocity. I'm thinking about it from the top. Its final velocity should be similar. The difference between these two is when it lands on the carpet, the cushioning of the carpet makes it take longer. The tiled floor, it hits and it cracks and it's broken. All right, so there are quite a couple of examples whereby increasing the time over which the momentum change occurs, you can end up producing something that has a lower force. There are a couple of cases where you actually want a greater force, although I've never seen any of them examined in a matric exam. And the one is if you're doing karate chops through wood, okay? You'll notice that that's a very short, sharp kind of movement because there it's the exact opposite. It's a case of you wanting, I'm just quickly trying to get all my razors in place. Cool, there we go. It's a case of you wanting to use the same change in momentum to create a larger force to break the wood. So you must make sure there that you use a smaller time. So these are kind of things that we look at in application questions. Just as a hint, if you're ever asked to answer a question which uses this relationship, most people are very quick to go and look at the fact that maybe we'll do the example of why does the cup not break on the carpet. So what we'd usually say is that the change in time, and please I'm doing this shorthand, you write it out properly, but the change in time is longer and therefore the force is smaller. What most of you forget to do is say that the change in momentum is the same. So you must look out, this particular mark is a very important one because often if this is out of 3, this is the mark that many of you forget to state. For you, it's obvious. You're like, well, the change in momentum is the same because it fell from the same height. But unless you state that fact, you're not going to be given the marks for knowing it. So you please need to make sure that you state that fact. All right. Ladies and gentlemen, I think I'd like to give you just one question on this, and then we'll do a leg stretch, and then we'll come in with a little bit of graphs and applications and things like that. Changing momentum and momentum questions are generally relatively straightforward. I find that where people go wrong is when we bring in the directions, which is why it's so important for us to practice specific examples. All right, so I'm going to quickly clear all of the drawings again. And we're going to deal with one that would be very similar, I guess, to what you'd have in a vertical projectile motion question. Okay, so quite often they link vertical projectile motion with a little bit of momentum here. Okay, and what they do is they'll have something like, I don't know, the ball falls. I'm going to make this vertical projectile motion as well, maybe. No, I'll be nice. A ball falls from a certain height h, and when it hits the ground, it's traveling at 25 meters per second. Okay. It then rebounds off the ground. Please, this is just for me to show that it's across. It will obviously rebound from the same position, and it rebounds upwards at 22 meters per second. I'm going to tell you that the ball object, whatever it is, has a mass of, and I'm going to do this in grams, be warned, 300 grams. Okay. We're told that the collision takes place over a time of 0.05 seconds. And the question here is for all of you to please calculate the force of the ball on the ground. All right, so ladies and gentlemen, I'm going to quickly pause this and I'm going to ask everybody to quickly work out a solution for me. Go for it. I didn't get that answer. Please note that the time is 0.05 seconds. The mass is 300 grams. You've got to convert your mass. Okay. All right. If you've got an answer, please give me a thumbs up. Cool. Well done. If your answer is bigger than 200 but smaller than 300, keep your thumbs up. Okay, good. Good, good. All right. Ladies and gentlemen, the answer that I got was 282 newtons up. Now, this is where people get confused. If downwards is positive, upwards is negative. My final, so okay, let's just quickly go. Our equation is F delta T is equal to, and I could have done the change in momentum, but it's actually probably easier for me to jump straight, not that last bit, to jump straight to there. Okay, so F delta T is equal to mass final velocity minus initial velocity. So the force, the time is 0.05. Please just be careful, make sure that your seconds never change into fives. My mass is 0.3 kilograms because it's 300 grams divided by 1,000. My final velocity is 22 meters per second, but it's upwards, which makes it negative 22. Minus is a minus. The 25 is the 25 downwards. And if I then multiply those two together, okay, sorry, subtract those two, add them together, times by 0.3, divide by 0.05, I get 282, but it's negative. Negative in this case means upwards. Can I quickly have a show of hands? Who got the same answer as me? Good. Now, I think I can assume here rather safely that the people who didn't get the same answer didn't get the same answer because they muddled up their directions. And I think there was someone who put up their hands to ask a question. Who was that? Just quickly ask. Okay, if you've got a question, you're welcome to put up your hands and I will get to answering it. All right. So my biggest assumption here is the two places you could have made a mistake. Wrong formula, but we've only just started this, so you shouldn't be using the wrong formula. Wrong time doesn't make sense. Not changing mass, maybe. Big errors are the directions. So the directions are the bits that people tend to overlook, to confuse, and to kind of, I guess, be silly about. All right. Now that we've just done one, I'm going to quickly do another example here, and hopefully you should all get it right this time because we just kind of hinted through it. So the second one, I'm expecting all of you to get right because you should, but this is how we learn. We repeat it again and again, and then we get it right. So this time I'm going to have the ball hitting the ground, but I'm going to put it on a trampoline, which is the one time where it may actually end up going up higher than it started. So I'm kind of dealing with something where it hits and then it goes higher than it started, just to make it interesting. The ball comes down. The ball has a mass of, let's make it 2 kilograms. It's a big ball. It's a person. No, it's a ball. Okay, we've got a ball of 2 kilograms traveling at, let's make it 17 meters per second. It's really fast. And then it bounces up at 20 meters per second. We're back to having this as a ball. Otherwise, it's traveling at 72 kilometers an hour, which is insane. Right, we're not really putting this on a real example. The time of contact is going to be 0.1 seconds. And your question is to calculate the force. Ooh, I just realized in the previous question, sorry, I may have done something wrong because I gave the force of the ball on the floor as downwards. That made sense. If I'd asked you for the floor on the ball, you'd have had to change your direction. No, ball on the floor should have been downwards. I think I gave mine as upwards. Sorry, I did do it wrong. So I was doing floor on ball, not ball on floor. Just pay attention to that. I think I actually messed that one up in the previous question, but I've just remembered now and pinpointed it. All right, so make sure that you read the question carefully. Sorry. So here your question is to please calculate the force of the ground on the object. Okay, in order to cause this change in momentum. Go for it. I'm going to quickly pause while we do this, and you can all hopefully get through writing up your answers. Okay, go for it. Okay, when you get to your answer, you can quickly give me a thumbs up. Okay, good. Good, good, good. Okay, so hopefully this one, you wouldn't have made the same mistake if you made it before. Okay, so there's just a question saying, how would the first question's answer change when answering with the ball's force on the ground and not the ground on the ball? The magnitude is the same because of Newton's third law. All that changes is the direction. Ball exerts a downward force on the floor. Floor exerts an upward force on the ball. Okay, so for this particular one here, if we look at what we've done here, our time is 0.1 seconds. Our mass is 2 kilograms. Now, I was naughty here. I knew that it was going to go upwards or the force is going to be upwards. So I just made upwards positive. Okay, you're allowed to do that too. So my direction of upwards was positive. You choose your direction. So over here, the final velocity was positive 20 minus the initial was negative 17. And I probably should have a second bracket there. Worked that out and got 740 newtons upwards. All right, ladies and gentlemen, can I quickly double check who got the same answer as me? Fantastic. Okay, I'd like to hope that the second time around gave you a chance to get it right, even if you hadn't got it right the first time. Okay, ladies and gentlemen, we're now halfway through the lesson. I'm going to ask you to just quickly stand up and stretch your legs. When you get back, we're going to be going through the conservation of linear momentum, which is where we have two objects collide. We say the sum of momentum before is equal to the sum of momentum afterwards. All right, so I'm going to quickly give you a chance to just stretch and do that, and then we'll come back in a second. All right, okay. Okay. Oh. Okay, ladies and gentlemen, there was one question here which said, if you made downward positive, would you still say upwards in the final answer? The point is that if you'd made downwards positive, your entire direction sign would change. So if I go back, I don't know if my whiteboard's still here. Cool. So if I'd instead, let's quickly look at the scenario. If I'd instead made downwards positive, then what would have happened is that this would have been negative 20 final velocity, and this would have been positive 17, which means that my answer would have come out as negative 740 newtons. But the negative still would mean upwards. So the direction doesn't change. It's just that you'd have had a negative en route. So you'd have had to interpret that negative in terms of which way around you had made your signs, which meant that in this particular case, the negative would mean upwards, and that would give us the upwards direction. All right, does that make sense? Okay. All right, so I said to you that we were going to continue here with our our law of conservation of linear momentum. Okay, so we are now moving on, just quickly checking, all right, cool, to the law of conservation of linear momentum. And this is one of our conservation laws. A conservation law means that something doesn't change. So it effectively remains conserved during a process, in this case, a collision. So the law of conservation of linear momentum says that the total linear momentum of an isolated system is conserved. Now, I just want to point out a couple of things. You need the word total, you need the word linear, you need the word momentum. If you leave off total or linear, it's not the same. You lose the mark, okay? And then we also talk about it being an isolated system. Now, what we mean by an isolated system is that there are no external forces, okay? That means that all of the forces that we're considering are part of the system. Now, I find this to be a rather sneaky thing to do, because effectively what it allows us to do is just to make the system as big as we need it to be to incorporate all of the forces. Ladies and gentlemen, in my experience, you do not get cases where linear momentum is not conserved. So if you've ever got a question and your options are the momentum is conserved, you go, yes, the momentum is conserved. You can almost say that without needing to look in detail as to what's happening. We don't deal with situations where momentum is not conserved during a reaction. Okay, now realistically, we can deal with unusual things where we can go and say, well, surely we've got to lose some of our momentum. Like I take a ball of clay and I throw it against the wall and momentum is conserved. But take it with a pinch of salt, momentum is always conserved. So What this means is if we've got a collision, it's usually a collision, the sum, that's the symbol for sigma, the sum of the momentum before the collision is equal to the sum of the momentum after the collision. Now, I know that different schools teach this formula differently. And the reason I'm saying formula like a formula is this isn't on the formula sheet. On your formula sheet, you've got the equation P is equal to mv. And on your formula sheet, you've got the equation F delta T is equal to delta P. And I think you've got something about delta P is equal to mvf minus vi. Okay? But you've got nothing about the law of conservation of linear momentum. So what I like to remind myself is that the sum of the momentum before is the mass plus the velocities of every one of the objects that exists before. And there may be 1 or 2 or 3 or 4 objects. We usually don't deal with more than 2 at a go. So I say that it's the sum of the momentum of as many of them as there are before, which you can say is initial, is equal to the sum of the momentum. So I'm now going to go, so this I effectively makes this initial velocity, initial velocity, initial velocity. Here it's going to be mass 1, velocity 2, mass 2, velocity 2, whatever their values are, final. Please note, you get a mark for stating either this or this. I usually recommend that I do both, but technically if you've got the sum of momentum before equals the sum of momentum afterwards, you get your mark. All right, then we break it down to what we mean. And lastly, we plug in all of our values, making sure very importantly that all of our velocities get the correct direction that they need. Now, I tend to like to draw pictures when I do this. So if I say I've got ball A and ball B, and then they collide, this is my universal symbol if they collide. And then afterwards, I've got ball A and ball B. All right, so over here, I can say that ball A maybe has a mass of 3 kilograms, and it's traveling at 2 meters per second towards the right. Ball B has a mass of 2 kilograms, and it's stationary, so its velocity is 0. They collide. After they collide, we don't lose any mass. It's very rare for them ever to let you lose mass in between. Ball B travels off at 2 meters per second. And my question could be, what is the velocity of ball A and which way does it go? I don't necessarily know which way it's going to go. All right. So what I would do from here is I'm going to quickly realize that I've got 2 objects before and 2 objects afterwards. So this equation works. Sometimes we have one object which splits apart into 2 objects, where the 2 objects afterwards, the sum of their masses is the same as the one mass before. So one big mass splits into 2 separate masses. I tend to call those explosions, 1 into 2. We also have situations where 2 objects, usually traveling in opposite directions, but they don't even need to do that, collide and they stick together. Okay, they quite often like to do this with cars. The 2 cars collide, their bumpers become entangled and they move off together. The important thing that you've got to realize is if you've ever got 2 parts together, they must be moving as one, which means that they must only have one velocity or the same velocity as each other. We'll do a couple of examples and we'll get into those ones just now. All right, so if we look at this equation, I'm now going to go and say mass 1, initial velocity 1, plus mass 2, initial velocity 2. Please note, you don't have to have exactly the same thing here. Some of you may have been taught slightly different versions. Here's mass 1, final velocity 1, plus mass 2, final velocity 2. Now what I'm going to do is I'm going to pick a direction as positive and stick with it for everything. My mass 1 is 3 kilograms. My initial velocity is 2 meters per second. My mass 2 is 2 and its initial velocity is 0. Please, we substitute in zeros, you don't get lazy. Over here, the mass over there is 3. We're looking for its final velocity, but we don't know what it is. I find that as soon as there's only one that I don't know, I don't bother with VF1 or anything. I just call it VF. Lastly, we've got our 2 kilogram object traveling positive 2 to the right. So 3 times 2 gives me 6 plus 0 is equal to 3vf plus 4. If I take this 4 back to the other side, I'm going to have 6 minus 4 is 3vf. Wait, I didn't do, yes, I did. Okay, so all of my directions, I did pay attention that that had to be a positive 0 and that this was a positive. I did it very quickly, so I didn't actually check it. So 6 minus 4 divided by 3 tells me that the final velocity that I get is going to be 0.67 meters per second. Since it is positive, that means that this object is still going to carry on moving towards the right. So its final velocity would be towards the right. Does this make sense to everybody? Quickly give me a thumbs up if it's all good and it all makes sense. Okay, brilliant. So I'm going to give all of you a couple of examples to practice like this so that we can check that you get the idea, and more importantly, that you can deal with scenarios where we suddenly don't just have, where we've got one and then it splits apart into two, those kind of examples. Okay. All right, so I'm going to quickly clear this. I hope everybody's got the definition down, and then we're going to get going. Okay, so the first scenario that I want to deal with is a train. So we have got a train and it's got two carriages that are joined together. Now we're pretending that this train is moving without an engine, so it isn't that anything's got an applied force that's keeping it moving. We're also assuming here that we're on a frictionless surface and that we can imagine away all of our problems. So effectively we've got two carriages that are traveling together at a constant velocity. This one has a mass of 500 kilograms. And this one has a mass of 800 kilograms because it's got more stuff in it. Okay. Then what happens is we have an explosion. Okay. Now the explosion can be anything that we like, but after, oh, let's make them travel. I actually wanted them traveling. I know I'm making this up, so please just bear with the fact that the numbers don't add well, the scenario is not so realistic. Now what I'm going to do is I'm going to say that there's a small explosion between the two. Literally something goes boom, and what happens is the one goes forward faster and the other goes backwards faster. Way more realistic in this type of example is rockets going into outer space. When we've got rockets and you know that your rockets break off and bits fall off as it goes, as they split apart, the one goes backwards and the other goes forwards, so that it goes forwards with greater velocity than it did before. Okay. We're going to pretend that this is a horizontal type of rocket question. I regard this as an explosion question. And over here, I'm going to tell you that this one now travels forward at 8 meters per second, very hypothetical. I would like to know the velocity of the 500 kilogram trolley. All right, ladies and gentlemen, I'm going to pause and I'm going to quickly give you a chance to all do this question. Please get started on it straight away. Go for it. So the question is to work out the velocity of the 500 kilogram trolley. All right. Ladies and gentlemen, if you've got an answer, please can I ask for a thumbs up? Okay, good. Good, good. Okay. Fantastic. So if I resume sharing, this is the answer that I got. Okay, so I ended up with an answer of 7.6 meters per second to the left. Can I quickly ask by show of hands who got the same answer as me? Yay, okay, that means mine's probably right. Okay, so ladies and gentlemen, this was an example of an explosion where you have one object going across to two. I'm going to do one last example made up before we move on to past papers. We should actually have a chance this evening to do some past paper questions. I'm also going to encourage you to go back to your vertical projectile motion questions, and you now should be able to fill in some of the blanks where you had objects colliding with the floor or situations like this. Sometimes they even represent this on a graph where you'll have an initial velocity, a final velocity, and a change in time. So it could fall under your vertical projectile graphs as well. Okay, so it is a possibility that you've got to read off the graph what the force change is. All right, last example, we're going to do this really simply. We've got a car of mass, I don't know, 3,000 kilograms, 3 tons, traveling at 20 meters per second. Sometimes they may also give this to you in kilometers per hour and you need to work it out. And we've got another car, these cars are going to take up too much of my page, traveling, there's a windscreen, at 10 meters per second, okay? And they collide, and afterwards the two cars stick together. Okay, so they mangled parts after the collision, they all stick together. And afterwards they stick together and they travel towards, you can assume no mass is lost. They're going to travel towards the right at, let's make this 50, that's a nasty number, let's make it 12. They travel together at 12 meters per second towards the right. Now I've kind of changed this question up a little bit. What I would like to do is I would like you to please tell me what is the mass of the second car. So it's a slightly different version of the same question, just to make it a little bit interesting. All right, so I'm going to pause sharing and I'm going to ask you all please to work out for me what the mass of the second car is, assuming that no mass is lost during the collision. Okay, little bit trickier, not very tricky, but a little bit trickier. As a hint, use M for the mass of the car you don't know and solve. Who has got an answer for me? Thumbs up if you've got an answer. Okay, fantastic. Who's got a reasonable answer, which means that your mass is bigger than 1,000 kilograms, but smaller than 2,000 kilograms? Most cars are 1 to 3 tons. Otherwise, we're dealing with like really heavy cars. All right. Ladies and gentlemen, that sounds about right. Okay. Okay, I can hear someone's background noise. That's very funny. Okay, not quite certain what happened there. Okay, now there was just a quick question here with regards to the directions that we use. And the question said, do they mind if we use west instead of left or east instead of right? Please don't. I would say direction of motion and opposite direction of motion, towards the right, towards the left. The thing you've got to realize is just because I point in a specific direction doesn't suddenly make it north, south, east, or west. You can't all look to your right and go, oh, wow, that's good. Okay, I'm looking towards my right. It should be the same for you. Go right will be east and left will be west. Please don't ever swap in left and right and east and west just because you feel that you can. If you do that, you're actually making it up. Okay, making it up is never a good thing. All right, so ladies and gentlemen, I'm going to quickly share my answer with you. Okay, so I got an answer once I plugged everything in. You'll notice I did something slightly different over here to what I normally do. And that's, well, what I've done up till now. And that's that I said, well, if they're sticking together, they've got the same velocity. I'm just going to add them together and effectively take out their velocity as a common factor. So then I multiplied out and I got an answer of 1,090,91 kilograms. All right, can I quickly ask who got the same answer as me? Thumbs up if you did. Okay, good. That question was slightly trickier, but I don't think yet impossible. All right, so I'm going to quickly stop sharing for just 2 seconds. I'm going to go and get a past paper type question for us to do together. And I'm going to go and get it out of one of my folders. So please bear with me for 2 seconds while I go and find one that's nice. Okay, we're going to do it. We've still got enough time to do it, so it's a good thing. I just need to make sure that I get a decent enough one for us to work from. And unfortunately, I didn't have planning time because I didn't know which section we were doing until we were doing it. Okay. All right, there's one. In fact, I'm just suddenly thinking my preparation that I did do a little bit of preparation, but it was for the wrong section. All right. There's my one question. Quickly getting us 2, and that should take us to the end of today's lesson. No, sorry. Okay. So this section's been rather nice and quick and easy, I think, today, which is a good thing. It means that we're, I think, getting a little bit more efficient at this. All right, so I've got a question for you. There we go. All right. Okay, let me quickly share the screen. Not that screen. Share that screen. All right, so ladies and gentlemen, here is our question for today. And the question says, one of the 2 questions for today. The question says 2 trolleys, X and Y, of masses M and 2M respectively, are stationary on a frictionless track with a compressed spring between them as shown in the diagram. When the spring is released, the trolleys move apart due to the force exerted by the string. The ratio of the magnitude of the momentum of trolley X to the momentum of trolley Y is. I'd like to remind you that X has a mass of M and Y has a mass of 2M. All right, I'm going to quickly pause this while I give you an opportunity to work out what you think the answer is. Please shout when you are sure you've got the right answer. Okay, so I want a thumbs up when you've got to the right answer. Okay, good. Well done. I see 2 thumbs so far. 3, 4. Good. Okay, fantastic. That looks good. I think I may even find this as being one of those that I actually am going to ask you to tell me what your answer is just now. Because it's a tricky one. All right, ladies and gentlemen, because I don't want to tell you what the answer is. I don't want to embarrass you either, but nobody will remember what your answer was, only you. I'm going to ask quickly. Who said the answer was A? You've got A as the answer. Please put up your hand. Okay, it doesn't look like anybody went for A. Who says that B is the answer? If you think that B is the answer, put up your hand. Okay, I can see about 3 people putting up their hand for B. If you think C is the answer, put up your hand. Once again, about 3 people, 4 people, 5 people for C. And 8 people for C. Who thinks that D is the right answer? Okay, I'm giving you a chance for D. Who has no clue what they're doing? It looks like the majority of you. I've got a bunch of people who don't think answered. So I'm going to quickly run in. The answer here is B. The momentum is the same. So they were initially stationary on the track, which means that your sum of momentum before must equal 0. That means that the sum of momentum afterwards must also equal 0. So this will have a momentum P and this will have a momentum P. Please, it is true that this will travel at a velocity V and this will be traveling twice as fast. But the question was for the ratio of the magnitudes of their momenta. All right, well done. I think there were only about 3 of you who got that right, who got caught up because they were too busy looking at the velocities and other things. They kind of got caught up in different traps instead of just looking at it and going, wow, the momentum before is this and the momentum afterwards is the same. Okay, well done. Well, I guess well done to a few of you. Well done to those of you that won't do this again. Okay. Last question that we're going to be doing for today. It is a little bit of a long one. Well, it's a bit of sorry, going very slowly. There we go. It's one that's rather nice because it involves a graph, so it involves a little bit of skills in terms of reading and application. Okay, let me just try and get the whole question squeezed in. It should fit. Okay, I think, yeah, that's the end of the question. All right, so ladies and gentlemen, the question here, and this is what we're going to end off today on, but it's still quite a nice question, okay, says, question 5.1, a 250-gram ball collides with a wall. The graph below shows how the ball's velocity changes with time. So its initial velocity is VI. We don't get told what it is, but its final velocity is 6 meters per second. We can assume that this is towards the wall and this is away from the wall. The ball's initial velocity is unknown and the force exerted by the wall on the ball is 450 newtons. The time of contact with the wall is 8 times 10 to the negative 3 seconds. The graph is not drawn to scale and you're asked to ignore the effects of friction. So question 5.1.1 says, what is the magnitude of the force exerted by the ball on the wall? All right, ladies and gentlemen, can I ask you, I'm going to actually ask, who knows what the answer is to the first question? Okay, that is correct. So because the question asked for magnitude, you didn't have to put in a direction, but if the force of the wall on the ball is 450, the ball on the wall will be the same. I'm not going to finish my sentence because I was about to give away the answer to the next part of the question. Magnitude means that we didn't have to say that the ball on the wall was towards the wall. We can get away without a direction. Okay, so question 5.1.2, name and state the law that you use to answer this question. Who knows what that answer is? what law did we use to say that the force of the wall on the ball is equal to the force of the ball on the wall? Okay, same person. We need other people answering. Yes. Yay. Okay. Now, please, in an exam, you've got to write it out in full, but it is Newton's third law. Now, a number of you, I guess, missed this. Name, 1 mark. State, 2 marks. So Newton's third law says if body A, object A if you prefer, exerts a force on body B, body B will exert an equal but opposite force back on body A. Please, if you use the word objects instead, I sometimes think it's preferable. Every time I think about the word bodies, A's and B's, I always think of little cadavers, but it's not a very, it's not a very common thing. It's just a morbid, yeah. All right, question 5.1.3 says use the information to calculate the ball's initial velocity. And I think that many of you should be able to do this. So what I'm going to do right now is I'm going to pause and I'm going to give you an opportunity to answer question 5.1.3 before I give you the answer. All right, so ladies and gentlemen, please get started on that right now. All right, ladies and gentlemen, can I please ask if you've got an answer to quickly give me a thumbs up? Okay, I'll give you longer. I'll give you longer. Must admit, it's sometimes a little bit unfair if I just get to the answer. I'm like, yay, we're all done. I'll give you a little bit longer if you need it. Okay, if you've got it, in fact, can I suggest if you've got it, quickly type it in just so that I can check. Make sure that mine's also right. If you look at the picture, it does look like VI is slightly, well, it's negative, and also looks like that it's slightly below where 6 would be. But remember, these are not drawn to scale, so you can't actually assume that. But usually they wouldn't make it smaller, like they wouldn't draw it like that, and then suddenly the value is smaller than 6. All right. I got a different answer to 1. Oh my goodness, this is going to be interesting. Yay, one person's got the answer as me. Whew. Okay, same answer. All right. I always get a little bit paranoid when my answers don't look the same. So over there, what I did over here, let's just quickly run through it. So F delta T is mVF minus VI. Our force is 450, and maybe I need to make sure that I'm doing the same direction here. The force is, now maybe I've got to be very careful. I've messed up on one of these before. Let me pause here. So I'm going to assume here that the final velocity is away from the wall. The force exerted by the wall on the ball will also be away from the wall. So that is the same direction. Please be careful. There was one of those recently that actually caught me out, where I just stuck in the force as being positive and I never thought about which way around it went. So the force here is away from the wall. This will have the same sign as that. Okay, so that's good. Then our time is 8 times 10 to the negative 3. That's fine. The final, the mass, you had to convert your 250 grams into kilograms, which I think most of you did. Final velocity is positive 6 minus initial velocity over there. Okay, I multiplied those two together and I ended up with 3.6. And then I multiplied this out here. The 0.25 times 6 gave me 1.5, and that gave me negative 0.25 VI. I took the 1.5 over, it became negative. And I had 2.1 is negative 0.25 VI. 2.1 divided by negative 0.25 gave me negative 8.5 meters per second, which made the answer 8.4 meters per second. 8.4 meters per second. And in this case, the question was the ball's initial velocity. If positive means away from the wall, negative means towards the wall. Okay. And then the last question over here says, besides friction, mention one other force that the ball, on the ball that is ignored in this situation. Can anyone think of a second force that acts on the ball that we haven't considered in this situation? Anyone? I'm sure somebody does know. There we go. Gravity. Okay, so please just something with regards to this. Don't write gravity, write force of gravity. Gravitational force. Or weight. All of those are options to describe your force. All right, ladies and gentlemen, I think that I'm going to kind of wrap it up from here because I think we've done quite a lot in one day. It's really nice, I think, when the sections have been done a really long time ago, because it actually gives you a chance, I hope, to have revised them and to make sure that you understand all of the little individual bits. All right.